On February 14, 1990, NASA engineers deliberately destroyed the ability of one of humanity's greatest machines to ever see again, not because it broke, not because something failed. They did it on purpose, 34 minutes after that machine took the last photograph it would ever take. We're talking about Voyager 1, a spacecraft roughly the size of a small car, launched in 1977 that spent over a decade crossing the solar system. On one single day that February, it turned its cameras around, looked back at everything behind it, and captured 60 photographs, 60 frames. That is the entire visual record of the most distant photo shoot in human history. And what those 60 images contain, and why NASA chose to blind the spacecraft immediately afterward, is one of the strangest and most quietly moving stories in the history of space exploration. Voyager 1 launched on September 5th, 1977, timed around something that only happens once every 176 years, a planetary alignment that let a spacecraft use one planet's gravity to slingshot toward the next, picking up speed without burning extra fuel. Doing that reliably, across billions of kilometers with 1970s computers, was one of the most ambitious engineering bets NASA ever made. It paid off almost immediately. Voyager 1 swept past Jupiter in 1979 and returned images nobody was prepared for. The Great Red Spot, a storm larger than Earth itself, photographed up close for the first time. The Moon, Io, revealed as the most volcanically active body in the solar system. Europa, showing a cracked icy shell that hinted at an ocean underneath. Every image rewrote a textbook. Then came Saturn in 1980, where the rings turned out to be thousands of individual ringlets rather than one flat disk, shepherded into place by tiny moons nobody had known existed, and where Titan revealed an atmosphere so thick with orange haze that the cameras couldn't see through it to the ground. After Saturn, Voyager 1's trajectory flung it up and out of the plane the planets orbit in, ending any chance of visiting Uranus or Neptune. That job went to its twin, Voyager 2, launched 16 days earlier. Voyager 1 had a different path ahead of it, a decade of nothing but empty space, heading for the edge of everything our sun touches. By 1990, it had been flying for over 12 years and was roughly 6 billion kilometers from home. Its power, generated by the slow radioactive decay of onboard plutonium, was fading a little more every year, permanently and irreversibly. Every system had to be rationed. Nothing got turned on without a calculation behind it. This is the moment one man had been waiting 9 years for. Carl Sagan, a planetary scientist on Voyager's imaging team and one of the most gifted science communicators of his era, had proposed something back in 1981 that most of his colleagues initially waved off: turn the cameras around. Have Voyager 1, from the edge of the solar system, take one final portrait, a mosaic of all the planets seen from the outside looking back in. The resistance to this idea was reasonable, not petty. The cameras had sat unused for years, frozen near absolute zero in deep space, and nobody could guarantee they'd survive being powered back up without their fragile internal components cracking. There were also doubts about whether the images would even be worth the risk. Tiny distant planets photographed from 6 billion kilometers out might just be shapeless blurs. And the cameras had never been designed to point anywhere near the sun's glare, which meant even attempting the shot carried a real risk of frying the sensors permanently. Sagan kept making the case, anyway, for years. His argument wasn't scientific, it was philosophical. No machine had ever gone far enough to turn around and see the whole neighborhood at once, including the little world it came from. That image, he argued, wouldn't add data. It would change how people understood their own existence. In 1989, NASA finally approved it, and the engineering that followed was brutal. On February 13, 1990, the team began a 3-hour warm-up sequence, easing power into the camera heaters so gradually that the sensors wouldn't crack from thermal shock on the way up from near absolute zero. There was no way to know if it had worked until hours later, when confirmation crawled back across 6 billion kilometers at the speed of light. Onboard memory was almost impossibly tight by modern standards, so engineers had to beam up an entirely new set of pointing commands from the ground, precise to fractions of a degree, aimed not at anything the team could actually see, but at mathematically predicted positions of planets that would show up in the final frames as objects smaller than a single pixel. Each exposure ran about 15 seconds, long enough to gather a usable signal from such faint light, but long enough that the spacecraft's own internal vibration could smear the image into a faint streak if the timing was off even slightly. Once captured, the photos were written to an aging mechanical tape recorder, and transmitting all 60 frames back to Earth at a trickle of a data rate would take weeks. The sequence opened with Neptune, a planet Voyager 1 had never actually visited. That was Voyager 2's territory, photographed now from a distance where sunlight itself arrives 1,000 times weaker than it does at Earth. The result wasn't a sharp blue sphere. It was a faint smear of light, a planet 57 Earths could fit inside, reduced to a smudge. Uranus came next, reconstructed from 3 separate color-filtered exposures into a similarly pale, ghostly point. the planet whose bizarre sideways tilt had made headlines during Voyager 2's flyby years earlier, now indistinguishable from a dim star. Saturn, the last planet Voyager 1 had actually visited up close, produced one of the more meaningful frames in the sequence. From 5.3 billion kilometers away, its ring still showed up as a faint but real thickening around the planet's disk, one of the only images in the whole set where you can actually tell you're looking at a planet rather than just a point of light. Then Jupiter, the largest planet in the solar system, big enough to swallow every other planet combined, appeared as nothing more than an overexposed dot. No storms, no bands, no great red spot, indistinguishable from a slightly bright star. The same planet whose close-up photographs had stunned the world 11 years earlier was now visually nothing at all. That's the core lesson sitting inside this whole sequence. Distance doesn't care about size or beauty. From far enough away, every world collapses into the same undifferentiated dot. 3 planets never made it into the final mosaic at all, and the reasons why say almost as much as the images that did survive. Mars was lost entirely to sunlight, a thin, dark crescent whose faint reflected signal was drowned out by glare scattering inside the camera housing. Mercury was deliberately skipped before the cameras even powered up, because photographing it would have meant pointing the sensors dangerously close to the sun itself, a risk NASA wasn't willing to take with the whole sequence still ahead of it. Pluto was ruled out mathematically before a single frame was wasted on it, too small and too dim to register as anything but sensor noise. These absences aren't gaps in the story. They're proof of exactly how unforgiving the conditions were. Then came the 2 frames that mattered most. Venus, wrapped in dense reflective clouds, showed up as a crisp, unmistakable crescent, the clearest image in the entire sequence, and a genuine testament to 12-year-old hardware still performing near the edge of its design. But Earth came just before it, and that photograph is the one that changed everything. At the moment of exposure, Earth was about 6.05 billion kilometers away. And from that distance, our entire planet, every ocean, every mountain range, every person who had ever lived, occupied about 1/10 of a single pixel on the sensor. Not a resolved image of a world. Just the faint diffraction pattern of an impossibly distant point of light. Aim the camera a fraction of a millimeter off, and there's no dot at all, just black. And by pure chance, not by design, the sun's glare was scattering off the camera's internal lens barrels that day, throwing a few stray shafts of light across the frame, and Earth happened to be sitting directly inside one of them. Our planet cradled in an accidental beam of scattered sunlight. Nobody planned that. It just happened to be true. What people now recognize as the pale blue dot is actually a composite 3 separate black and white exposures shot through different color filters, painstakingly combined back on Earth months later to approximate what a human eye might see, with the blue tint coming from the wavelength our atmosphere and oceans reflect. When Carl Sagan first saw the finished image, he understood immediately that it wasn't a data point, it was a mirror. He later wrote about it at length, making the case that everyone who had ever lived, every triumph and every cruelty in human history, had happened on that single, fragile speck suspended in a sunbeam, and that recognizing how alone and small that speck really is carries a kind of responsibility to take better care of each other and of it. At 4:48 GMT on February 14th, 1990, the shutter closed for the 60th and final time. And fittingly, the last frame wasn't a planet at all. It was mostly noise, scattered light and static, an unceremonious ending with no dramatic final shot. And then, 34 minutes later, came the decision that made it permanent. Voyager 1's entire onboard computer held roughly 68 kilobytes of memory, less than a single low-resolution photo on a modern phone. Every byte was precious, and the spacecraft's next mission phase, crossing into interstellar space and measuring the magnetic fields and particles out there, needed software that simply couldn't fit in memory alongside the imaging system. So NASA engineers overwrote it. The code that had captured Jupiter's storms, Saturn's rings, and the pale blue dot itself was erased permanently. Voyager 1 didn't lose its cameras. It forgot how to use them, and there has never been a way to put that code back, because there's nowhere left in the spacecraft's memory to put it. Shortly after, the camera heaters were shut off too, to reclaim every last watt. And without regulation, the cameras plunged below minus 200 degrees Celsius, freezing solid, almost certainly cracking at the molecular level. They're still bolted to the spacecraft's instrument boom right now, pointed in the exact direction they last looked in February 1990. Not sleeping, not dormant, dead. And that sacrifice bought Voyager 1 roughly 40 more years of life, enough power margin to survive crossing the termination shock in 2004 and reach true interstellar space in 2012, becoming the first human-made object to ever leave the solar system's bubble. If the cameras had stayed on even a few extra months, the spacecraft might never have made it that far. We traded its eyes for its reach. Today, in 2026, Voyager 1 is more than 24 billion kilometers from Earth. A signal from home takes over 22 hours to reach it. Only a handful of instruments still function, measuring magnetic fields and cosmic particles from interstellar space, and the team keeping it alive is still pulling off remarkable feats on 50-year-old hardware, reactivating long-dormant thrusters in 2025, using decades-old blueprints, and working around a corrupted memory chip in 2024 to restore full data transmission. The dead cameras remain fixed in place, looking at nothing, capable of looking at nothing, standing as physical proof of a single day when humanity turned around to look at where it came from before stepping permanently into the dark. In roughly 40,000 years, long after its power has run out completely, Voyager 1 will drift within about a light year and a half of a distant star, carrying with it the golden record, a message about who we were, mounted right alongside two frozen, cracked cameras that no longer work. The record tells whoever might find it what we sounded like and what we looked like. The cameras tell a quieter story, that we weren't content just to live on our small, fragile point of light. We wanted to look back and see it for what it actually was, once before the lights went out for good.